So first things first, I'm going to do a quick little review on logic gates and we'll go from there. So the first gate we're going to be doing is known as an AND gate. You got an input AB and an output of a Y. And the table for that is just simple 0 0 0 1 1 0 1 1. You got an output of Y. So you have an output of 0 everywhere except for when both A and B are high, a 1, you get an output of a 1. The Boolean expression is just A dot B, or you might just see it as AB. Now its counterpart is what's known as a NAND gate, and you have a bubble in front of the gate, or you might have it at the input of A and B, and the table for that will be the exact opposite. So when it's in the 0 0, you'll get a 1, 0 1 you get a 1, 1 0 you get a 1, and when both are high you get a 0. So it's the complement of the AND gate. It will be written as AB bar, or you might see it as A prime B prime. Now we're going to be looking at what's known as an OR gate, and you have the input A, B, and the output Y. We're going to draw the table for it. So you write out the table, and for an OR gate, whether the input A or B is high, so a 1, you'll get an output of a 1. Both are low, you get a 0. So everywhere is a 1 except for the 0 0 state. You'll see it as A plus B equals Y. Now you have its counterpart with the bubble in the front. Again, you can have the bubbles in front of the input in the A and B, and that's known as a NOR gate. So the NOR gate is the complement of the OR gate. So the truth table for that will be the complete opposite. So you'll get a 1 when in the 0 0 state, a 0 everywhere else. You might see it as A bar plus B bar, or you might just see it as A prime ORed with B prime, and you get a Y. Now we'll look at what's known as a NOT gate, and it has a bubble and a triangle, an input of an A and an output of a B. So the truth table for this is fairly simple. When the input is 0, the output is not a 0, so it's a 1. When the input is a 1, the output is not a 1, so it's a 0. And you'll just see this written as B equals A bar or A prime. This next gate looks a lot like an OR gate, but it has an extra line in the front. So this is known as an XOR exclusive OR gate, an input of an A and a B, an output of a Y. So now we're going to go ahead and write the truth table for this. For this XOR exclusive OR gate, it will be an output of a 1 when one of the inputs is high, so a 1. So in the 0 0 state, you'll get a 0, and in the 1 1 state, you'll get a 0. But in the other two states, when one of the inputs is high, you get a 1 output. And then you'll see it written as A circle plus B, indicating that it's an exclusive OR gate. You might also see it as A bar B ORed with A B bar. You might see a prime instead of the bar, but it's essentially the same thing. Now we'll look at its complement, which has a bubble in the front. So now this is known as the XNOR gate. So as expected, you will get the same truth table, but reverse. So in the 0, 0 state, you're going to get a 1, and in the 1, 1 state, you're going to get a 1. But when only one of the inputs is high, you're going to get zeros for those two states. So it'll be just like the XOR, except the zeros and ones are flipped on the output. I think it's also good to go over a tri-state buffer. And tri-state buffer, there's 4 different states. You'll be seeing it as an input, a control, or a clock, and an output. You'll see its other form where it has a bubble near the output. And then we're going to go ahead and do the truth table. I'm going to put it as C to the -1, stating that it is its counterpart. So I'm going to write it like this. Now for a tri-state buffer, when the both inputs are low, you get an output, a high Z output. When you have the control as a 1, what it does is it turns it on, so that means it will just pass whatever the input is. So since the input is a 0, it just passes a 0 to the output, and then when both the control and the input are 1, that means it's going to just pass whatever the input is, which is a 1, so you get a 1 in the output. And its reverse, everything will be the same except for the 0 and 1 state, they get flipped. And these two states are known as the active high for the tri-state buffer. Now there are 2 other ones where you have a bubble in front of the control or the clock, and then you also have another one where on the output and on the control you have bubbles. And then this is known as the active low state for the tri-state buffer. We're going to go ahead and do the truth table for this. Now, as you'll notice, for this active low state, the Z's and its outputs are reversed from the active high. So wherever there was a Z, now it is a 0, and wherever there was a 1, it's a Z now. So it's just what the active high was, just the place of the Z changes out. So now when the control is low, it will pass whatever the input is. Now it's time to go over what's known as the nMOS transistor. For an nMOS, when you see them in parallel, that means that it represents an OR gate. And when you see nMOS in series, it represents an AND gate. For pMOS, when you have them in parallel, it will represent a NAND gate. And when you have pMOS transistors in series, it represents a NOR gate. So for nMOS, when the gate input is a 0, that means it's off. And when the gate is a 1, that means the transistor is on. So looking at this little diagram, this is what an nMOS transistor looks like. You got the drain, source, and the gate. So when you're passing a 0 to the gate, it means the transistor is off. You're passing a 1, it's on. For the pMOS, it's reversed. When the gate is passing a 0, it means it's on. And when the gate is a 1, it means it's off. And you'll notice on the pMOS, there's a bubble in the front, which states that it's reversed. Now in digital circuits, you have two parts where you represent nMOS and pMOS as CMOS. You have a pull-up network and you have a pull-down network. You have your input and you have your output. Now in the pull-up network, it's pMOS transistors, and in the pull-down network you have nMOS transistors. So you do this based off of what I wrote in yellow on top, and you represent the output in CMOS. So you have a combination of nMOS and pMOS, and you get an output of CMOS. Now let's say, for example, we are to represent a 2-input NAND gate in its CMOS representation. So for NAND gate, you're going to be in the pull-up network, you're going to be putting two pMOS transistors in parallel, and in the pull-down network, you're going to do the complete opposite. Since the transistors are in parallel, now you're going to be putting two transistors of nMOS in series, and that's how you represent a NAND gate. But let's say now you want to represent an AND gate. So an AND gate would be a NAND gate, but with a NOT gate in front of it. A NOT gate is just a simple inverter comprised of one pMOS in the pull-up and one nMOS in the pull-down. And all you do is you just stick this in front of your NAND gate, your 2-input NAND gate, and now it's an AND gate. Now you're representing a 2-input AND gate. Now the same concept. Let's say you want to represent a NOR gate. For a NOR gate, it's the opposite. So for a 2-input NOR gate, for the pull-up network, you're going to have two pMOSs in series, and now you're going to have two nMOSs in parallel in the pull-down network, and that will represent a NOR gate. And again, the same thing. If you wanted to represent an OR gate, all you would do is stick an inverter in front of that, which comprised of one pMOS and one nMOS, and you just stick that right before the output, and now your new output is on the right of this inverter. And now what you have done is you've converted the NOR gate into an OR gate. So I'm going to start with this easy problem. This is a Boolean function, which is an A prime ORed with B prime and ANDed by C. So what you do first is you take the complement of that. So everywhere there was an OR, it's ANDed, and everywhere there was ANDed, it's ORed, and also the operations also, you get the complement of its operation. So what you do here is you're going to be putting the A and the B in parallel because they are ANDed. In a pull-up network, when they are ANDed, you're going to be putting them in parallel. And since the C prime is ORed, you're going to be putting that in series with the A and B for the pull-up network. And when you go ahead to do the pull-down network, it is the complete opposite. So wherever they were in parallel, now it's in series. And wherever it was in series, now it's in parallel. So what we do here is we put the A and the B in series now. And we represent that with nMOSes. And now you put those two in parallel with the C prime, and you represent that with an nMOS. You ground it, you have your VDD up above C prime in the pull-up network, and your output will just be the original function, and that will be right in between the two networks. Now I'm going to show a medium problem where the function is equal to A ANDed with B ANDed with C, and that whole thing is ORed with D prime. Now you're going to take its complement, so A will be ORed with B, ORed with C. Don't forget to put the prime or the bar above those. And since those were ORed, now they're going to be ANDed with just a D since it was a prime in the original function. So now we're going to go ahead and put the A ORed with B ORed with C in series in the pull-up network, and we're going to represent those with pMOSes. And since that whole three thing are ANDed with the D, that means in the pull-up network it's going to be in parallel with those three, A prime, B prime, and C prime. So you're going to put the D there in parallel. Now this is for your pull-up network, and now when you go ahead to do the pull-down network, it's just going to be the opposite. Since the D was in parallel, now it's going to be in series. And since your A, B, and C were in series, now all those three will be in parallel. Now it will be in series with the D in the pull down network. We're always going to draw our line for the output in between the two networks, and our output will just be the original function that we were given. Now we're going to do one more function, and this is a little bit harder. We have the function A ORed with B ANDed with C, and C is ORed with A ANDed with D prime. So we're going to go ahead, take its complement. So wherever they are ORed, it's ANDed. Wherever it was ANDed, it's ORed. And also wherever they were prime, it's not going to be a prime. And if they weren't primed, they are primed now. So we're going to go ahead and do this function and convert it. So since the A and B were ORed, now they're going to be ANDed and they're going to be primed. And since they were ANDed with the C, now they're going to be ORed with C on this left side. And the C is going to become a prime. And now that's going to be ANDed with A or with D, since in the original function they were ANDed. They no longer are primed. So I like to always start up with the pull-up network, which comprised of pMOS transistors. And we're going to go ahead and begin with that. So first we're going to go ahead and draw the A ANDed with B in parallel. Now since the C is ORed with those two, that means we put that in series. So we're going to draw that. And now we see that the C bar is ANDed with the A or D. So that means that the C has to be in parallel with those two. And since those two are ORed, that means you put those two in series. And now you just connect it all together to complete the pull-up network. We finish this problem by now doing the pull-down network, and in the pull-down network everything is reversed and replaced with nMOS transistors. So since we saw that the A and D were in series, now they are going to be in parallel with one another. And we also see that the A bar and the B bar were in parallel, so those will now be in series in the pull down network. And we see that those two were in series with the C bar, so now they have to be in parallel with one another. And we draw that, and this will complete your pull down network. And your output will always be in between those two networks, and you get an output of your original function, which was f equals A ORed with B ANDed with C, and then that C was ORed with a D bar, which were ANDed.